just want to mention that your second homework assignment, so that's due next Tuesday. So next Tuesday is the day that we have an exam. So that's an exam day. So I think we're going up to entire chapter 3 and of the chapter 4, so 4.1 through 4.4. So that's your plan so far. So today's Wednesday, so I'm a little behind, a day behind, so I'll go probably a little bit of 4.1 up to that, so we'll see how it goes. But anyway, all these assignment questions, you should be working on them as we move on. So they're all due on Tuesday or the day of the exam. So you're the only one? Okay. All right, so let's see. I would like to, let's see. Okay, so let's start at 3.8. So it is a little easier than doing all these multivariate distributions. So let's talk about 3.8, which is a functions of a random variable. So let me start 3.8.1, which is a random variable with a discrete distribution. So let's start with a discrete case and moving on to a continuous case. So random variable with a discrete distribution. Let's go. So what's the goal of this particular section is simple. So it says something like this. What am I going to be doing on this particular section is that you're going to be given a random variable, let's say given a distribution. Whether it's continuous or discrete, you're given a distribution and you're trying to figure out the distribution of the function of x or g of x. So that's a goal. So make it simple. For example, if my x is a random variable which is uniformly distributed, so it's any particular number that you can select from A to B, and the question is asking you, can you get me the distribution of, let's say, 2 times x? So that's what we're doing. So starting with the discrete case now, so let's look at the discrete case. I'm going to be starting with the theorem to show you how to get this distribution. So the theorem 381. So it says x is a discrete random variable and it has its own probability mass function. So with PMF, let's call that f(x). So we write this subscript x because this is about an x random variable. So what we want is the probability mass function of some function of x. So let's say let's call that y variable, which is some function of x. And the PMF of the function of x is f of y. So this is about the random variable y. And by definition, this is the probability that your y variable takes a number small y, which means the probability that your y variable is a function of x, is g of x, equals to some number y. So this is a probability mass function for a function of x. So therefore, all I have to do is to get my the PMF of y, so f of y, I have to get all these probabilities over here. So I get all these x's so that g of x equals to y. I want all those x values and I want to add them up. So I have to get all these probabilities for all these x values that satisfies the g of x equals to the number y. That probability of this x random variable. So this is how you get your PMF, which is not bad if you actually do the probability and the distribution with the actual example. So let me get the actual example. So that's my theorem. Skip this. All right, let's get a simple case of this. Let's get the PMF of x. And let me do this PMF as a table form. So my x is a random variable. It takes the numbers -1 or 0 or 1 or 2. So one of the 4 possible numbers, and each one has its own probability. So let's get the probability of each number. So x of 1, the probability is 2/8. 0 is a 1/8. Then 1/8 again, and 2 is 4/8. So 2 is a lot more likely than the other 3 numbers, according to this. So I want my random variable, let y be x squared, a function of x. So I'd like to determine the PMF of y. So let's start from there. So if my x's are -1, 0, 1, and 2, the y values are, you get the y values by squaring your x values. So if I think about it that way, I should be getting the y values is one of those 0, or it can be 1, or it can be 2. So we are trying to determine probabilities of 0, 1, or 2. So let me get it. So properly, let's get f of y. So I have to go start one by one. I want f of y 0, and I want f of y of 1 and f of y of 2 to get complete distribution. So f of y equals to y of 0 means the probability that your y random variable equals 0. But now my y is x squared. So we're going back to x random variable. So we are trying to get all these x values. And when you square that, you get the value 0. So there's only one of it because I have -1, 0, 1, and 2 for x values. So it can only be x equals to 0, which is f of x of 0. So I'm getting 1/8. So that's my probability for y value of 0. So I'm going to be doing that right away. I create a table as I move on. So let's get the PMF of y, which is x squared. So simply, let me create a table also, and I know what my y's are. So it will be one of those 3 numbers, either 0, 1, or 2, and the probability, I just figured out the 0, which is 1/8. Got this? And I have to finish the rest of it. So now let's moving on to the next probability that your y variable equals to 1, which means x squared equals to 1. So I have to go get all my x values. When you square this, you'll get 1, and there are 2 of those. So now I have to add those 2 cases, either x equals to -1 and plus x equals to +1. So that's what I mean by you add all these x values where the function equals to 1. That's it. So I got my values of f of x -1, and I have to add +1. So that should be 2 of those, this and this, so that 3/8. So that gives me 3/8 for that y value of 1. And I want to complete the rest, which is pretty, I think it's not 2, my mistake. It shouldn't be 2. Let me fix that. It should be 4. So let me get my y value of 4. So y equals to 4, which means x squared equals to 4. And for my x value, there's only one x that gives me square of 4, which is x equals to 2. So that's my f of x of 2. So that's 4/8. So now I'm getting y value of 4. That should be 4/8. So this is a complete probability mass function. So for a discrete case, it's not that bad. I just have to go through the numbers one by one. Should be okay. Now for a continuous case, it's a little different. So we have to go through a little different process. So I want to go through the continuous random variable. So that's my second subsection 3A2. So how do we do if the continuous random variable, a function of that, so random variable with a continuous distribution. All right, let's go continuous case. All right, so before I do, I'd like to remind you, because things are a little different, I have to do some integration done. So let's recall, let me just remind you. If a x is a continuous random variable, your cumulative distribution function, big f of x, is the probability that your random variable x is less than or equal to some number x. Now, if x is a continuous random variable, then x or smaller is exactly the same as x is less than some small x. It's because for a continuous random variable, there is no probability for a single value. So it doesn't matter, it's strictly smaller or smaller than or equals to. So I'm going to mixing it up because it doesn't really matter. Now I want to go the other part, the opposite of this, the probability that your x is greater than some number x or greater than equals to, doesn't really matter. It is 1 minus the complement, which is x is less than or equals to some number x. So when I get x is greater than the number, it's 1 minus the f, the CDF of x, which is pretty commonly used. Let's have that ahead of time. So let's work on it. So I want to give you 2 examples where the function can be increasing or can be decreasing. Let's get either one of those or both of those. So starting with this example. So my x is a continuous random variable. And this one has PDF f of x. And let's get CDF also. Big f of x. So some function for PDF and CDF, the cumulative distribution function. So I'd like to know, let y be a function of this x, which is, let's say 2 times x. So in this case, I'm interested in a function g of x being 2 times x. So that's what we're doing. So we're interested in a distribution of this g of x. And I just want to mention this. This is an increasing function. So let's start something from the beginning all the way. Let's get the distribution. So I want determine the PDF of this y random variable. So let's go start from the scratch. Here we go. So I'm going to be starting from CDF. So probability that's f of y. So I'm interested in the cumulative distribution function of y, which by definition, probability that your y is smaller than or equal to some number y. Then I can replace my y with 2 times x. So y equals 2 times x. So 2 times x is less than or equal to some number y. Then I can divide both sides by 2. So I'm getting the probability that your x is less than or equal to y over 2. So I started with the CDF of y random variable, but at the end, I end up with the probability that your x is less than or equals to y. So time to do some integration then. So now I have to go integrate. So this is about x random variable. So I have to use the distribution of x. So I have to go get my f of x. So I have to go integrate all the way up to y over 2 from negative infinity with respect to x, which is, by definition, exactly same as the big F of y over 2. So that's what I'm getting. So this is my CDF. I should be getting PDF, but let's leave it there. I just want to make it a little gentler. So when I do my PDF, I'll do it in a minute, but leave it there. So what I want to do is I want to think about this as a general form. So let's imagine something like this. So if I want f of y, and your y is a function of x, so instead of having it 2 times x, I'm going to replace it as there's a probability that your y being less than or equals to y, which is function of x, g of x is less than or equals to y. So instead of having exact function of 2 times x, I'm interested in the g of x, and I'm assuming this g of x is an increasing function at the moment. So let's say that g is increasing function, strictly increasing. So if that's the case, I can change my probabilities as I did it. So I can go inverse of this for each side of it. G inverse of this and G inverse of this. So I can go through this, which is what I just did with the numbers there. So I'm getting, so function itself is increasing, the G is increasing. So my probability that I can get your x, let me use the same color. So that should be x is less than or equal to G inverse of y. So what we did up there is nothing more than this is my g of x, which is 2 times x is less than or equals to y. And this is my g x, which is, this is my g inverse. So your inverse function of this if I have my g equals to 2 times x, then g, the inverse of it is 1 over x over 2. So that's my g inverse is about, is y over 2 of y. So I'm just making it to be a little general. That was it. So now this is about x random variable. If you less than or equals to this, so by definition, this is your big F of x of this g inverse of y, which is exactly what we had up here. So this is my g inverse of y. So that's basically it. So now if I want my PDF, so f of y, the small f, so f of y is you take the derivative of big f of y, so CDF, to get your PDF. So I'm not going to be doing this right now, but you have to go get your derivative, ddy, your big f y over 2. Let's leave it there just like this. So that's how we can get this. We will have the actual function of it, so let's leave it there for now. So I want to go get another one, which is a decreasing function to get a feel for this. So my x is a continuous random variable. And the PDF is f of x, and CDF, big f of x. So this time, let's y variable equals to 1 over x. Let's be a little specific for x to be greater than 0. So that's my support. We always consider the positive side. So let's get this. So I want my 1 over x. So I want the distribution of this. So I would like to determine the PDF of this 1 over x. So again, let me do the same process. So I start from the CDF of y. By definition, it's the probability that your y variable is less than or equal to some number y, and y is 1 over x. So I can replace it with 1 over x is less than or equals to y. Then I would have it my x back. So let's get my x. Then I have to switch the inequality. That should be greater than or equals to 1 over y. So now I'm getting, well, isn't that 1 minus? So I'm integrating 1 over y to infinity, if you think about it. So I'm integrating the values from this to infinity for your PDF of x. So if x is this or greater, and I saw that up here, if I'm interested in something, x is number and greater, which is exactly same as 1 minus f of x. So that's exactly same as 1 minus f of x, which is greater than or equals to 1 over y, which is 1 over y. So this is it. So it's relating your x and y together. So I want to make it a little gentler. So I have this function 1 over x. So this example up here, your g of x was increasing function. Now this example, let me bring it down. And I want to bring it down. So this your g of x is 1 over x, for x to be something positive, which is a decreasing function. And it's a decreasing function. If I look at this inverse of that function, the g inverse, it should be 1 over x. So that's exactly what we have gone through in the process. So if I go through the same process of general g of y, g of x, let's go the same process as this. So f of y is a probability that y is less than or equals to y. Then y is g of x less than or equals to y. Then I'm going let's call, I think I said it clear, g is decreasing. Are you with me so far? So now I'm going through the process of this. So this is my g of x. And I go the inverse of that. So this is my g inverse of y, which it happens to be 1 over y in this case. So that I'm getting your x is greater than equals to this g inverse. So let me do the bracket, which is, it's about the CDF, it's 1 minus your f of x, g inverse of y in general. So when I get my TDF, I have to take the derivative. So f of y is the derivative of your CDF, so a big f of y, which is the derivative of this whole function, which is in this case 1 minus f of x 1 over y. So that's general form. So let's make the summary of this. So I want to make the summary of this. So what does that mean? Let's get summarized what we have it. So let's get x is a random variable. With its CDF. Let's use the PDF and CDF too. PDF, f of x, and CDF, big f of x. So let y be some function of x. The function is continuous, and it's either strictly increasing or strictly decreasing. Either way. So if that's the case, your PDF of y, so f of y, equals to, you take the derivative of your CDF of y with respect to y. So now I have to think about what happens up here. So let's go, when your function is increasing, I have right here. So I'm going to take the derivative of this f of y. So I need to go take the derivative of this. Are we okay so far? So let's do that. And this is it. So when I do the derivative for increasing function, so use the chain rule, you get the derivative of this big F becomes PDF of x. So I'm getting the derivative. Let's do it over here. Let's write it properly. So that becomes the derivative of f of, let me go back up here again. This is my derivative for increasing function here in general. So f of x, the CDF of x, and G inverse of y. And if I have a decreasing function, then I'm getting d with the derivative of this function, which I just showed you up here, which looks like this. So that's what I want. I want to take the derivative of that function. So 1 minus the f of x and G inverse. Or at the end of this, if I do this, so this is when G is increasing. When G is decreasing, strictly decreasing. However, at the end of this, we get the same thing. If you take the derivative, let's start with the increasing case. So you're going to be getting the PDF of x of G inverse of y, and you times by the derivative of G inverse. So that should be it. So that's your PDF of a random variable. Oops. Now if I go to the second one of the decreasing function, instead we get negative up here in front of it, and you take the derivative of this, so that at the end of this, your derivative will be a negative number. So that negative together, at the end of this, I can make it to be a same one expression in that way. So that this one will become positive if G is increasing, and it's negative if G is decreasing. So inverse is also decreasing. So that negative number in front of negative number together is really positive anyway at the end of it. So this is like a simple form to get your PDF of a function of x. Looks messy, but that's a fact at the end. Let's write them out as f of y. So you can use this theorem as it's a separate theorem. You can use it as it is, or you can just do it properly in the beginning. Matthew, do you have any question?
Yeah, I'm a little confused on how we jump from that piecewise function to the one with the absolute value.
From here to there?
Yes.
So I just did it, you can do it separately. So if I'm having the increasing function, then I'm simply having the f of y will be the derivative of this, the CDF, which is this, and you times by the derivative of this inner function G inverse. That should be it. If the G is decreasing, then your f of y, you will get, because of this negative, you get the negative of f of x, G inverse of y, and then times by the derivative of G inverse of y, and that G inverse of y, that's a negative number because G is a decreasing function. So what we're trying to do is that's negative. We have a negative in front together. It's positive, so I can just make it to be absolute value and drop the negative. So that's what it is. That makes sense? I can make it in a single formula in a sense to get the PDF.
Okay, I see what's going on. Yeah, thank you. I forgot the chain rule. That's all.
Oh yeah, it's the chain rule. I'm applying the chain rule. Inner function derivative. All right, I got this. So this is my function of x, and I want to try to figure out the PDF of a function of x, which is a little different from the PMF. That's easier. PMF is always simple. You get a bunch of numbers, add them up, and that's it. But it's not the same. So what I want to do is I would like to make this as an example. You don't have to use this particular theorem or the formula. In fact, you can actually process it one by one. So let me just do that. Before I go into the actual example, I'd like to discuss one more time about one of the special distribution, which is exponential distribution. It comes up so often. So let me say one more time for the special distribution, which I did it last time, but let me mention it one more time. Let's go with this exponential distribution. So last time I have introduced this exponential distribution, and it has one parameter, and it can be either one of those. So I think I said, where was it? I used either beta. I don't know exactly when I did it. It was the marginal somewhere. I'm pretty sure I did it. Maybe it's at the beginning of that lecture last time. Bivariate? I don't think so. Give me one second. I want to show it to you anyway. Maybe this. I'm pretty sure I discussed the exponential. This special right here. Here we go. So we have a special distribution. This exponential distribution, and we could have a parameter beta. Some books use it, and some books use lambda. So it's the same thing. It's one over the reciprocal of the other one. So I am going to be using lambda and use that expression because it's a little simpler to handle. So let me introduce that exponential distribution. So x is exponential with parameter lambda. So x is exponential distribution. It has a distribution with the parameter lambda. What does that mean? That means it has a PDF. So let's get the PDF of x. So PDF of this exponential distribution, it looks like this. It's f of x equals to the lambda times e to the power of negative lambda times x. X being greater than 0. It's PDF of an exponential distribution. Let's be clear that lambda must be positive. Some number. Not only this, I'm getting my CDF of x, and it's a closed formula, in fact. So that CDF of x, which is this, which means I'm trying to find a probability less than or equal to some number. Let me have a formula in a minute. Instead, let me just briefly show it to you. If I want f of a, for example, f of a, let's take it a. So I'm trying to figure out x is less than or equal to some number a. So I'm trying to integrate this exponential function from 0 to some number a of this lambda times e to the power of negative lambda x dx. So when you do this, which you will be able to get 1 minus e to the power of negative lambda times a. So it's pretty often, it come up often, so I just want to make use of it. So I don't have to do this integration every single time. So if I want x is less than or equals to a here, then you would integrate from 0 to a, which you'll end up with 1 minus negative lambda times a. So this is basically it. can make the formula out of this. So this is going to be 1 minus e to the power of negative lambda times x, which means if I'm interested in the probability that x is, the exponential, is greater than equal to a or greater than a, it's 1 minus the CDF. So it becomes e to the power of negative lambda times a. So I can just use it, so I don't have to worry about doing this integration every single time. So it's pretty common that you see something like this. So let me do an example with exponential. So I want to go x is a continuous random variable with its PDF as this. So PDF was f of x equal to e to the power of negative x for x greater than 0 and 0 otherwise. So you should realize, oh, isn't that this exponential function? So you kind of see this, oh, isn't that this f of x being the lambda of 1 times e to the power of negative 1 times x. So this is, in fact, the PDF of exponential distribution with lambda equals to 1, in fact. So I have an exponential distribution. So I'd like to know, let y be 1 over x. And I want the PDF of y. So let's get it. All right, so I'm going to just do it properly without using the formulas. Do it properly. According to this, for x greater than 0, for x variable, what it means is your y values, which is 1 over x, must be also greater than 0. So your distribution of y should have values 0 to infinity. So that's what it says, a support of y. I got this. So let me go back to f of y, which I think I kind of saw it already up here. I worked on 1 over x case already over here. So I got this, f of y, and this, and this, and this. So I have done this already. So I'm going to be just copying this because I've done it already. So let me copy this. So that happens to be the probability that your x is greater than or equal to or greater than 1 over y. So from the previous example, so now I'm ready to go do my integration, which I don't even have to. So remember, this x is what I have to use, which is exponential distribution. If I have to, what it means is I have to integrate your density function e to the power of negative x with respect to x going from 1 over y to infinity. Which you can do it, or, well, I know I've done this so many times, so I can make use of this right away. So it must be e to the power of negative lambda times the number a. So in this case, I know that I'll be getting this e to the power of negative lambda is just 1, so I'll have 1 over y. So that's my value, and that's my lambda times that number for y values greater than 0. So I'm done. I'm ready to go get my PDF of y, which is the derivative of this CDF, which we just did it, e to the power of negative 1 over y, and this is it. So I have to go the chain rule again, so e to the power of negative 1 over y taking the derivative of negative 1 over y. So you're getting 1 over y squared for y being greater than 0. So this is it. So I didn't have to use any of the whole formula up there, but you can if you want to. But I think it's a little easier to go through the process one by one. So let me just do couple more cases and I'll stop there for this section. So let's get uniform. X is uniform from 0 to 1. And let y be negative natural log of x. And I have to find the PDF of y. All right, let's start from here. So for x's are from 0 to 1. Then I need to know what y values are. So y is negative natural log of x. So your natural log function from 0 to 1, you have to kind of picture the natural log function from 0 to 1, which is, or you can go with negative natural log of x function. So natural log function from 0 to 1 is all the negative from 0 to negative infinity. The negative of that, which tells me that your y values are greater than 0. So that's a support of the y values. Got this. So I'm ready to get my f of y, which is the probability that your y is less than or equals to y, which is the probability that negative natural log of x is less than or equals to y. So now I can go divide both sides by negative first to get natural log of x is greater than or equals to negative y. And then e to the power of something. So undoing the natural log. So let's do that. So that gives me, so I'm going the e to the power of this and e to the power of this, which is increasing function. So I'm getting x greater than equal to e to the power of negative y. So this is it. So I just have to go get my probability, which is this. This is my PDF of x from 0 to 1, and it's constant, it's 1. So that's my PDF for 0 to 1. And I want this probability that the number starts from this to infinity, which I don't have to go infinity, it has to go from this, e to the negative y, to 1. So I want that probability, which is the area of the rectangle, anyway. So if I have to go properly, you have to go from this, e to the negative y, up to 1 of your PDF, which is 1, dx. So you should be getting the base of this rectangle, 1 minus e to the power of negative y, and height is 1. This is the area of the rectangle. So this is my CDF. Let's bring it down. Then I just have to get my PDF by taking the derivative. So dy 1 minus this. So that should be e to the power of negative y. So properly, your f of y's are where to where. You have to tell me exactly. Y is greater than 0 and 0 otherwise. So I kind of did it properly and formally in that way. If you want that formula, you can use it also. This is my one. I can do it this way. Just find the process of doing this. Number 2, you can use, what am I using? You can also use what I did it up here. So using this f of y equals to the f of x with g inverse of y times this absolute value of the derivative of g inverse of y. Can be done. If that's easier. All right, so let's get this. The g function over here is natural log of x with a negative, so negative ln of x. So I have to go get my g inverse, which is e. Let me get this inverse of y. So it will be this. And the derivative of this g inverse of y, which is negative e to the power of negative y. So if I'm using that theorem there, it will be this is f of x. F of x is always 1. So that's 1. Times the absolute value of this, the derivative of the g inverse, which is negative of this. So you will get the same e to the power of negative 1. Will be done the same way. But I think this is a lot more confusing, so I think it's better to go follow the process and go through it rather than just using the formula or theorem. Are we okay so far? Alrighty. So let me give you a break. So I think we need some time. So any question you have, you can ask me. Otherwise, let's have about 6:25. Let's about 5 minutes of break. So start at 6:30. At 6. right, it's 6:31, so let's get going. Oh, let's see. So I think I did, where was I? So I kind of finished two examples, one with exponential and one with uniform. So you could do either way during the process of doing the CDF, and you derive it all the way, or you can use the theorem right away. So I want to go, let's see, I want to go this example. And let's say I have a PDF of x. It's given below. Let's get the PDF of x is this. So f of x is 1 plus x over 2 for x values from -1 to +1. So my support is from -1 to +1. So the graph of the PDF of x, it goes from -1 to +1 and 0 everywhere else, like this. So that's the PDF of x, is f of x. So I want my y to be, let y being x squared. So in this case, your function g, the function of x, is x squared. And unfortunately, this is not strictly increasing or strictly decreasing. So we have x value from -1 to 1. So it's decreasing from -1 to 0 and increasing from 0 to 1. So I may not be able to use that formula right away. So it's just a lot easier that you go through the process. So this is not strictly increasing or decreasing. So I want to go through this process. So let's get the determine PDF of y. I feel it's a lot easier to go through the whole process. So remember, again, x values from -1 to +1. That tells me your y values, let's do this, y is x squared. So y value should be going from 0 to 1. So that's my support of y. So my y will be defined over that value from 0 to 1. So start from the CDF always. So let's get f of y. By definition, it's the probability that your random variable y is less than or equal to the number y. Then time to replace my y with x squared. So now I need to go get my x squared is less than or equals to some number y. And I want my x, so let's do the square roots. So I'm getting the probability that your x squared is less than or equals to y. Y is a positive number anyway, so it goes from negative square root of y to positive square root of y. So it becomes this. So it's just becoming that you integrate your PDF of x. Here's my x variable. So I'm using the PDF of x from negative square root of y to positive square root of y of your PDF of x, which is 1 plus x over 2 dx. So I'll let you do the rest of the work here, and if you do complete this, you will get square root of y. All right, so now this is my CDF of y. So I have to get my PDF of y. So let's get f of y, which is the derivative of this square root of y. So that means 1 over 2 times square root of y. So properly, if I have to say my f of y looks like this. For the support, you have to be careful. What is my y values? The y values are based on this from 0 to 1. And 0 otherwise. So that's a function. But it's a lot easier to go just follow the step and we'll get it. So I think that was the whole case where you don't have this strictly decreasing or increasing function. So I can just do it anyway, either way. So that was that. And let me get to the last theorem, the last step there. So I'm getting 382, which is about linear function. So x is a continuous random variable with PDF of f of x. So I'm interested in a function of x, but it's a linear function of x. So let y be a times x plus b. So a is not 0. If that's the case, then the PDF of y is the following. So f of y equals to 1 over absolute value of a and f of x y minus b over a. Again, you can try to prove this, which can be done. So you can think about doing this quickly. Your y is ax plus b. So which means your function g is ax plus b. So your inverse of the function g is x minus b over a. So if I replace it with y, if inverse of y, which is y minus b over a anyway, b over a, and your derivative of this g inverse is 1 over a. So using that whole theorem, which can be done, so I can get my f of y equals to the derivative, the f of x of that g inverse y minus b over a times the derivative with absolute value. A can be positive, it can be negative. So let's get either positive or negative, so absolute value of that. So that's basically it. So you can actually do an example on your own and think about this, but I don't want to do another example. So I think this is the end of 3.8. So function of a random variable, and we're getting a distribution of that. So moving on to 3.9. It's not just function of x alone, so we have function of 2 or more random variables. So I have to consider more than just one random variable. So let's do simply. So let's get discrete first and continuous. So starting from 391, so let's get random variables. With a discrete joint distribution. Let me at least write them down and go from there. So let's say something simple, the sum of just two random variables. So let's start something simple. So we have x and y, and they have a joint PMF. So that's my f of x and y together. And what I'm interested in is, well, let another variable, let's call z, equals to the sum of these two, x plus y. Then I'm interested in the PMF of this z. The probability mass function of this random variable z, which is created using x plus y. So starting from the beginning, so I'm starting from f of z is having a number z. They look the same, but it's one is big, one is small. Which is the probability that this random variable z will take a number, something smaller, value of z, something like this. And then the variable z is x plus y equals to some number z. So it's going back to x plus y, which means the joint. So we have to use joint PMF to get this probability. So which means I have to add them up, all these xy's. So whatever the xy's are, such that your sum of those two numbers must be equal to the number z. And I want all these x, y pair to get all the joint probabilities all together. So that's what it is. So at the end of this, whatever the z is, it's going to be a number. So we're interested in adding all the probabilities. So I can use my x equals to some number, but your y variable is z minus x. So x plus y must be that number z. So y must be z minus x. So I can use all these x values from where to where, depending on the support, from negative to positive infinity, whatever that is. So this is basically it, which is about adding your joint, which is x, y. Your x is x. Your y value will be z minus x for all these x values from negative to positive infinity in the general concept of it. But that's anyway, that was this. So I don't want to go into too much details of it, but I want to make it something that's pretty useful and pretty famous. So let's go through the binomial. So let's go start 392. So not only that we add x and y, we can have many more than that. So let's start with 392. So we have x1, x2, and dot, 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 xn are IID. I don't even want to write dots. Let's just do IID. Random variables. Having means each one having a Bernoulli distribution. With the parameter p. So I have introduced IID last time, independent and identically distributed. So I think I was looking at it right before this So I think it was right there, IID. We did right here. So we may have a sample is taken from a population, for example. So all of these random variables are independent. They have the exact same distribution. So that we call IID, independent and identically distributed. Independent, having the same distribution, that's called IID. So that's where we are. So now then, what does that mean? If that's the case, let's get this. Then I want to call, let Y be some of these n random variables. X1, X2 plus X3 dot dot dot, xn. Then it says this Y has the binomial distribution. With parameters N and P. So I don't want to prove this theorem, but I want to think about this idea of this theorem. So let's consider the following. So let's make it simple. So I want to consider a simple case. So let's say we have X1, X2, X3. Let's make 10 of those. They're IID with any random variable. So each one of those, Xi, is either 1 or 0 for every single one of them. So if it's success, so I pick an item, it's defective, that's success, for example. And failure, then it's 0. And the probability of X equals to 1, that's small p. And the probability of X equals to 0, that's a failure probability, which is 1 minus p. For all these, I goes from 1 through n. IID means they all have the same distribution. So what they say was Y, which is sum of these random variables, dot, 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 up to X of 10. So I want to do it as conceptually, not mathematically. So this is what's happening. So I have an item, and that item is either success or failure. Success means that's a defective, and failure not defective, whatever that is. So X1 is a random variable, and it tells me whether it's 1 or 0, bad or good, success or failure. X2 is about the second item, whether it's bad or good, success or failure, 1 or 0. And the same way, I go through every single one of them. It can be 1, it can be 0, and that's it. So I go all the way up to X of 10. Again, we have 10 different items, and one can be 1 or 0. It's all random variable, and it's all independent. According to this, your values of X1 can be 1, can be 0. I don't know which one, but let's make it up. So it can be 1, for example. So it's success for the first one, first item. And the second one, it's 0. It's a failure. Third one, it's 1 again. And fourth one, 0 and 1 and 0 and dot, dot, dot. I go up to 10. So what it says is, what if I'm adding all these numbers together and plus and plus and plus all this? So we're simply adding ones and zeros. So when you get the sum of all these, this is my Y. So that Y becomes nothing more than how many ones? How many successes in 10 of those items? So that basically happens this. So if I'm interested in, for example, probability that your Y equals to 8, it means there are 8 ones and 2 zeros. That's what it means. So 2 of those are zeros and 8 of those are ones. So when you add them out, it should be 8. So that's what it means. So therefore, finding the probability is simply this. So out of the 10, which of the two are 0, which of 8 are successes. So I'm getting 10 choose 8. And success means probability of P out of 8. There are 8 of those ones. And the failure, 2 of those squared. So this is binomial. So in particular, y equals to 8. So I can make it to be a general case. So how many ones, in fact? So nothing more than that. So that y value is nothing more than number of ones, number of successes in 10 of those items. So therefore, in general, what's going to be happening? You get your f of y. So in general means, let me try to get down over here, your y being x1, x2, and x3, dot, 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 x of n. So n of those items, and all of these are 0 or 1. I can think of it that way as an n of those items. So it can be 1, it can be 0. So I'm interested in how many ones, how many zeros. So this is nothing more than a binomial. So y is binomial of how many successes and how many failures. So n trial to n items and success probability of P. So basically this is what happens. So sum of this Bernoulli random variable, binomial. So that's what's happening. So each one is x1. So I'm looking at how many ones, how many successes. So that y become total number of ones, number of successes in a sample of n, or in n trials. So that's what we see as a binomial. Well, since I mentioned this, I'd like to get even more general than this. So let me go conceptually. My xi's are, they're all having binomial, but it's not their new random variable. It's binomial with ni number of trials, with success being P, or I goes 1 to up to, let me use different letter, let's call M. And these x1, x2, all these random variables are independent. They're not identical because we have different n's, they're independent. So they're independent but not identical. But according to this, I can call this y being sum of these random variables. And conceptually, again, I can imagine my number of items. So I can go the first n1 items or trials, and how many ones, how many successes, that's my x1. Then I have another set of items, so think of it as n2 of those items, and how many ones, how many successes in those items, that's my x2. So by doing so, I can imagine all these number of items or trial go all the way up to x of m. A set of trials and how many successes. That's my x of m. So when I add all of these random variables all together, I'm simply counting how many ones in this, how many ones there. So I'm simply adding ones and zeros. This is my 0, 1, 0, 1, all the way, like this. So I'm simply adding them up all together in that sense. So I'm trying to count how many successes in total of these. So it's again another binomial. So that y is binomial. So sum of binomial is a binomial. How many total trials? We have n1 of those plus n2 of those and 3 of those. So we have total n1, n2, n3, all the way of m of n. So the total of this many trials, the sum of these n i's, I goes from 1 to m, and success doesn't change. So n is p. It becomes binomial. So that's also general facts about binomial. So now I'm done with this. This is my discrete case. So let's moving on to continuous case, which is 392. So this is the random variables. With a continuous. Let me see, what did I call? Let's say continuous joint distribution. All right, so let me go the definition. 391. It says there are two random variables. NX2 be independent random variables. So they're independent. They may not be identically distributed, but they're independent. So let y be the sum of these two numbers, x1 plus x2. So the distribution of the sum of the two continuous random variable is a convolution. Of the distributions of these two random variables. So I'm interested in the sum of the two. That's a point. Okay, let's get the definition out of it. So let me try. I think the book might have given you the formula there, but I don't want to do that. So let me just give you the actual case rather than doing the theorems. Let's get the example in the book. 394. So let me see. So let me call. In the book, X is exponential distribution with lambda being 2. And y is also exponential with lambda of 2. And x and y's are independent. So I'm going to use w. Z is kind of confusing. Let's use a w. Sum of these two random variables, x plus y, and determine the distribution of w. All right, so let's get ahead. So I want to recall, let's note that. So f is exponential, x is exponential, which means f of x with lambda 2, so 2 to the power of e to negative 2x, for x being greater than 0. And the same thing for f of y is exactly the same, exact same expression, except the variable is y, for y greater than 0. And let me even do the joint. XY together. Well, joint is the product of the two, since they're independent. So we have 2 times e to the power of negative 2x, and f of y, 2 times e to the power of negative 2y, for both x and y's are 0 or greater. That's a joint. And recall that if I have x, which is exponential, so remember, x is less than or equal to some number a, it was 1 minus e to the power of negative 2, in that case, a. 2 is your lambda, so that's your a, and that's your a. I don't know if I will be needing it. Let me see if I need it. So just in case, and x is greater than a, that is e to the power of negative 2a, so I can just use it when it happens. That's an a. Well, I got all of these, so start from, Grace, I got this. So let's start from the CDF of W. So let's start with W. So let's go from big F of W, which is by definition, probability that is random variable W is less than or equals to some number W, which is the probability that your sum of the two random variable is less than or equals to W. Got it. So I'm ready to do this integration. So this is my joint. So after is my joint distribution. So remind you about the support of x and y's. So x and y, the support will be all these part over here. So it should be x and y are both 0 and infinity. So this is my support. All this first. That's where. So now I have to go get my probability. So imagine it's like a doubling number. So I can imagine x plus y is less than or equals to some number 2, for example. If that's the case, how would I go by this probability? So I have to go think about this line, y equals to negative x plus w. So I have to go get this probability. So that's my w somewhere, and that's the line of x plus y equals to w. And I have to get the probability over that region here in that support. I'm ready. So I'm ready. So here we go. So that's my W. And this is my W, whatever the value is. So I have to go integrate my joint PDF. So I have to go all the way. So I have to go again, either way, I want to go 0 to W for X. Then your Y goes from 0 to W minus X. Again, I have to go think about integrating. So whatever the X is, your Y goes from 0 to Y goes W minus X. So that's all I'm doing in the joint. The joint, I got my joint up here, which is this. So 2 times, I want to copy as it is, e to the power of negative 2x, and 2 times e to the power of negative 2y, dy dx. Then I'm almost done here. So let's go the outside. Got this outer integral. Got this. So I have to go look at this y's alone. So I'm looking at the y's. So these are the y's. So I want to keep it there. And 2 times e to the power of negative 2x. Let's keep it outside. So let's do the integral from 0 to w minus x 2 times e to the power of negative 2y dy dx. So now let me use this. This is exponential. We lambda of 2. And I know how to get the probability of this from 0 to some number w minus x. So according to this, if I have an exponential distribution, I'm integrating from 0 to something, so I want to have something like this. Here we go. So x2, or in this case y, but up to some number a, the number a becomes, that's my number a. So I have this expression that I can just use right away. So that becomes 0 to w. So that inside integral, that becomes 1 minus, and I replace this a with the whole w minus x with a negative 2w minus x dx. So I think this is it. So just have to do a little more integration. So if I do separate these over here, let's just write one more time. 0 to w 2 times e to the power of negative 2x. So this is 1 minus e to the power of negative 2w and positive 2x dx. So when I multiply it out, then you will get 0 to w 2 times e to the power of negative 2x. Then subtracting, when I multiply this times this, so that and that will be gone. So I'm getting this one, that's going to be e negative 2w dx. All right, so therefore, I'm almost done here. So therefore, I want to separate them out. So from 0 to w, 2 times e to the power of negative 2x dx, and then 2 times e to the power of 2w and dx, which is a constant. So from 0 to w. So here it goes again. It's just like the probability that your x is less than or equals to w. And I saw that expression already up here, right there. So that becomes 1 minus, right there, e to the power of negative 2 times w. And then the other side, this is there's no x there, there's a constant. So we get w minus 0 times this. So we get 2w e to the power of negative 2w. So this is your big f of w, all the way down. And the derivative. So f of w is the derivative of this whole thing. So I have to do the product rule and dot, 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 which you can do it. So I'll let you get the final version of it. So you will get 4 times w e to the power of negative 2 times w, for w being 0 to infinity and 0 otherwise. So this is a convolution. A long way to go, but this is it. And this is a very special distribution. It's called the gamma distribution. Are we okay so far? So that was that. So that's your sum of the two random variables. So let me then introduce one more thing that'll give you a break. So the next one is the order statistics. 3, 9, 3. So I don't think the book is giving you actual definition of it. So I'll just leave it as order statistic. So in particular, we are interested in minimum and the maximum. So let's get order statistic. So we're not doing anything other than that. So we just want the minimum and the maximum of a random sample. So let me introduce what it means and how we write them typically. So we have a random sample, a sample taken of size n, a random sample of size n is selected from a population. So in short, we say this as your x1 is the random variable of your interest, x2 the random variable of interest. So we have total x of 1 through x of n, their IID. They're independent and identically distributed, with each one has a PDF, exactly same PDF. Let's use f of x, and exactly same CDF, which is big f of x. So what is the order statistics? The order statistics are you would rank these numbers, or you arrange them in order. So we write them down as x with 1 in parentheses, which is the smallest of these n values, and x with 2 in parentheses, second order smallest values of it, and dot, 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 all the way up to x of n. So the values are in order, smallest to the largest. So this is the smallest, the minimum. This is the largest, the maximum. So that's how we typically write them down. So what it means is your x of 1 in parentheses is a function of these whole thing. Let's get 1. Is the minimum of x1, x2, all these n random variables. It's a function of these random variables. And x of n, which is the maximum of these random variables, dot, 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 x of n. So it's a function of these n random variables. So it may not be kind of clear what I mean by this. So let me make a case. So for example, what I mean by this is I'm just making a case. Let's pick 3 numbers. So x1, x2, and x3, they're all independent. And their IID. Let's do IID. With uniform. On a set of numbers 1, 2, 3, 4, 5. Equally likely. So any number can be a number for each of these random variables. So for example, I have random variable x, and you did a selection of 1 through 5, any one number, which happens to be number, let's say 2. Your second random variable, pick any number at random out of this 1 through 5. It happens to be number 5. And third variable, we pick a number, it happens to be number 1. So we typically call these small x1, small x2, and small x3. That's how we write them down. So order statistic means of the 3, the smallest value of the 3, which happens to be 1. So your first order statistic, that's going to be 1. And your second smallest number, that's going to be 2. And the third, in this case, the largest of the 3, that's going to be 5. So you have them, the smallest and the second smallest and the third, one by one. So that's called order statistics. Are you with me so far? So that was that. It's 7:18, so I don't think I can do. I think it's better that I give you a break now and then do an example and complete this in one whole sitting. So why don't I have a little break at 7:18, so 18, 20, 25 ish. Let's get 10 minutes of break. So let's start at 7:28, 5-8-ish, then I'll finish the rest of it. That's better.
I have a quick question.
Uh-huh.
So for the equals 5, does that say x3 equal to 5, or does that say x?
It's not x3 equals 5. So according to this fake data, for example, x1 is 2, x2 is 5, x3 is 1. But order statistic means which one of the 3 is the smallest. So this is smallest, so we call the first order statistic value is 1. The second order statistic, the value is 2, which is this number. And the third order statistic, which is this number 5. So the parenthesis means give me the smallest of the 3, and second smallest, and the third smallest. So that's what it means.
Okay, thank you.
Mm-hmm.
Professor, I have a question.
Uh-huh.
Okay, on the homework list, there is no homework assigned from 3.9, but there is one from 3.11, and so does 4.9, which are not lecture planned. So are they
I was going to be checking the questions. They're a little more complicated than I was hoping. So they're not the right level of question that I'd like to have you do. So I checked today. So 311 is supplementary questions. So the questions in 3.11 covers all the topics from 3.1 through 3.10, all the way.
Okay, so do you still want us to do 3.11 and 4.9 even though it's not directly covered?
There is no homework question from section 3.9.
No. So do you still want us to do 3.11 since it's a review?
Right. So 3.11 is the combination of all the sections all together. So those are the good questions. Yes.
How about 4.9?
4.9?
Yes.
I said 4.9 is also the supplementary questions. It's as far as I remember, 4.9 was I don't have a 4.9. I think 4.9 would be supplementary. So the 4.9, as far as I remember, the 4.9 has the questions related to the first 4 topics, 4 sections.
Okay.
I think so. That's how I did it. Mm-hmm. 4 points. I don't have any. Oops. Right. Here we go. So this 4.9 is supplementary exercises. This is coming from the topics from the first 4 sections. So that's what I have it up there. Mm-hmm.
Professor, I have a question.
Mm-hmm.
Yeah, so since 3.9 doesn't appear on the homework too much, how much do we expect it for the exam?
How much means as much as I do in classroom, not more.
Okay.
Mm-hmm.
Okay, sounds good. Thank you.
Mm-hmm. Oral statistic? Mm-hmm.
You go back to the part where you had the inverse functions.
The functional variables?
Just one where you were saying the marginal is equal to the CDF times the absolute value.
This one?
Yeah. This X,
Mm-hmm.
this is ET, or yeah, I was going to ask if it needs to be.
In that expression?
Or, yeah, do variables need to be?
Yes. Jeez. So discrete doesn't have to go that far. Discrete is very simple. Which is something like this. With data function, discrete is counting possible numbers. So that was way simpler. You can get it to see. Mm-hmm. So which ones are giving me that x squared? So that was way simpler. Continuous is not that simple. So we're starting in about 2-3 minutes. We're done, or you're going to keep it there? Mm-hmm. Mm-hmm.
Trying to think about why.
Why? Why is that so, or why?
Or why, what the formula is saying.
It's sometimes it's kind of intuitive. Sometimes it's not easy to kind of see the meaning of it, as it says. Mm-hmm.
I guess what is the derivative of the inverse signify?
The derivative of the inverse?
Or the derivative of g of y. I guess what
Yeah, because you have the functional x. This is not just the derivative is a function of x. So I have to also think about the derivative of that. I don't know if that's what you're thinking. So it goes of something like this. So if you go, your x value is not, your y is function of x. You have to go think about the derivative. After when you take the derivative to get the PDF, you have to take the derivative of that inner function. So that was okay. It's about 27-ish. Mm-hmm.
So it's like getting the probability of x being a certain number,
Mm-hmm.
and you multiply it by the change, or like how that changes. And then you put, sorry.
Okay, that's right. Think again. So I'll also think about this. So it's 28-ish. So why don't I get you? I think I want to go just one of it to see the use of this order statistics. So let me go and do. I think I will start with the example and then give you the general form of it. So I want to go get this example. It's a very common example with this order statistic. So we have a system. So it's like a circuit board or something. So some connected in series and parallel. So let's get the system. It has 5 parts or components. And they're connected in series. So we have a component. Think of it as a component here and there. They're connected in series like this, dot, dot, dot. So you can think about the electric current going from this in that direction, from this to this. Let me make a couple more components since we have 5 of those. So from here goes there. So I have a current goes from one to the left to right. Then the system has 5 different components, and these components function independently. It can fail, it can work. So the component function independently. All right, so since the system it has 5 different components connected in series like this, then the entire system will fail if any one of the 5 fails. All right, so I can call component 1, so the failure time being x1, and the failure time of this is x2 and dot, dot, dot. So I can imagine let xi being the failure time. So how long does it take until it fails? Let's call this in hours of this ith component. So it can fail anytime. So let's say, to make it simple, I want to go, I goes from 1 to 5. So we have x3 can fail anytime, 4 and x5. Then this x1, x3, all these are IID. They all have the same distribution. They're all independent. So let's say, make it simple as IID exponential with lambda being 2. So what it means is this distribution of x is 2 times e to the power of negative 2x, for x to be greater than 0. So what I want is the component, the component of the system itself. So let's call y being the system's failure time. So if I say it that way, well, it's easy. The system fails as soon as one of them fails. So whichever the 5, which has the smallest failure time, it fails the first, then the system fails. So this y is nothing more than the first order statistic, whichever that fails the first. So that's how we use this order statistic. So let me get some probability as a practice. So find the probability that the system fails. How likely is it that this entire system fails in 30 minutes, in half an hour? Alrighty, so that means, so I want the probability that your system failure time is less than 1/2, so in 30 minutes the system fails. Alright, so then I want to go kind of opposite, and you'll know why I do that way. So I want to go 1 minus probability that y is greater than 1/2. It's because, let's write them down, this 1 minus the variable y, which is the first order statistic, and I know what it means. It means the minimum failure time of all these random variables. So that means your y variable, which is the smallest of these x1, x2, all of those x of n, is greater than 1/2. So now that makes it simple as the smallest of this is greater than 0.5, then all of them must be greater than 0.5. That's what it means by the first failure time of the first component has to be longer than this 30 minutes. Also, the second longer than 1/2. So everything has to be longer than 1/2. So I think I have 5 components. Let's get 5. So that's what it means. The shortest one, it failed in, let's say, it lasts longer than 30 minutes, which means everything has longer than 30 minutes. So what I'll do is now I'm going to be ready to get my probability. So let me separate them out. So I can separate all of those into probability that x1 greater than 1/2 times x2 greater than 1/2 the product of the probabilities, because they're independent. So now I'm ready. So every single one of them right here, they all have the same expression. So remember, again, this is exponential distribution. Your x is greater than 1/2. Let me remind you again, when I see the distribution of exponential, I have, where was it? It was somewhere, I think over here. Exponential, right here. So your exponential, your x is greater than something. This is your expression of this 1 minus CDF. So 2 times, got this. So we have this has to be 1 minus, it's greater than, so greater means it's exactly, did I say 1 minus? It's less than or equals to, let me get back, it's right this. I want to use this one, it's greater than. So So e to the power of negative 2a, which is a lambda of 2 in that case. And I think I have a lambda of 2 also in this case. So that means I'm getting e to the power of negative lambda times that number a, which is 1/2. So that's my first one. Then the second one is exactly the same. They all have the exact same distribution. So that's the same. And I have 5 of those. So that's exactly the same. So I have 1 minus e to the power of negative 1 and to the power of 5, pretty much. So negative 5. So you're getting, the chance of that happening is 0.993. So very, very likely the system will fail in 30 minutes. But that's what it means. Are you making sense here? So now that I've gone through this, why do I go through this? Because I want to think about the PDF. Let's find the PDF for y. So I've gone through all these already. So here it goes. Let me copy this. Big F of y equals to, here we go. I got all the way. Big F of y, this is my F of y, pretty much the CDF. It equals to all the way down to this over here. So this is, in fact, let me just be clear. So this is nothing more than f of 1/2. So that's what I have it. So at the end of this, I'm getting, this is exactly same as this over here. So 1 minus this and this, the same thing 5 times. So I'm getting 1 minus this. I have it right there. E to the power of negative 2 times lambda times is there. So I have y, which is your value. If it's easier, you can go through this as probability that your y is less than or equals to some number y, which equals to this. I don't think I need this. And then I have to go get 5 times. So e to the power of this is one of those. And I have 5 of those. So this is it. So therefore, I should be getting my PDF. The derivative of this. So this is in fact 1 minus negative 10y. So that should be 10 times e to the power of negative 10y. For y being greater than 0. So smallest order statistic, that should be also 0 and greater. So this is it. So according to this, I got this. And I hope you might notice this also, that this isn't that exponential. So this is your lambda. And e to the power of negative lambda times the variable. So this is in fact the exponential. So I do notice that your smallest order statistic in this case, it is exponential with lambda being 10. So I think that's how we do the probability in the PDF. So what I want to do is I want to make a general form for the largest and the smallest. So here comes the order statistics. So let's get this. Let's get the PDF. Of X and the largest and the PDF of the smallest. Let's get them. Let's start from here. We want to go with the first, the largest order statistic. So I think I've given you a little bit of concept there. So I can imagine X1, X2, Xn are IID. They all have the same PDF and same CDF, big F of X. And let Y being the largest order statistic, which is the maximum of them. So let's get the PDF. So I want to start from my CDF, F of Y, and the probability that your Y is less than or equals to Y. And I know my Y, which is the max of those n random variables. So I'm trying to find largest of them is less than or equals to some number Y. The largest of them is smaller than Y, then everything else is smaller than Y. So that's what it means. So it means that everything has to be smaller than or equals to Y. Dot, dot, dot. X of n smaller than or equals to Y. And they're independent, so I can separate them out into X1 less than or equals to Y times dot, 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 Xn less than or equals to Y. So each one of those, they have the CDF. This is my F of Y. F of XY, let's be clear. This is F of X. And every single one of them, we have the same CDF, which means this times power of n. So now I'm ready to get my PDF, which is the derivative of this CDF of Y. So that should be n times this F of X power of n minus 1 and the derivative of the CDF of X, which is the PDF of X. So that should be your order statistic for the maximum. Then let me repeat the same thing for the smallest order statistic. So let's get PDF of the smallest order statistic. Exactly same setting. So we have IID. With the same PDF, same CDF. So I'm not using X there because it's kind of clear, but that's what it is. So now I'm going to be letting Y being the smallest order statistic, which is the minimum of all these random variables. And I kind of did an example like this, starting from this F of Y, which is probability that your Y is less than or equals to Y. But when you do the minimum, I have to go, everything is greater than this. So we have to consider greater. So I want to go complement of this. So 1 minus probability that the Y is greater than some number Y. So So y is the minimum of all these random variables. So that means the same thing. Everything has to be greater. So that means x1 is greater, x2 is greater, and I want to separate them out because they're independent. So therefore, this is 1 minus f of y for x random variable. So now I'm getting, let's get this a little lower. It is 1 minus f of y for x random variable, and we have n of those, power of n. So that's my CDF. So I want to get my PDF. So if I go the derivative of this, let me just do it right away. So you're getting n times this whole thing, power of n minus 1. I forgot the negative because I'm getting my negative when I do my derivative of the inside. So you're getting f of y. So this is it. This is your smallest order statistic. I don't want to do any more than that. So this is it. So the example that I did it was a system was having components that are connected in series. So as soon as the smallest one, the one that fails the first, the entire system fails, then I can go thinking about the system in components are in parallel. I don't want to do this, but I want you to think about this. So we have a system that's connected in parallel, like components are connected in parallel, like this, and da da da. So that the current goes from this to that. So as long as one works, the system works. So entire system failure time. So this is my x1, how long it takes to fail, x2, x3, dot, dot, dot. The entire system failure time. So that system fails when everything fails. All of them fail. So what it means is, as long as one functions properly, entire system will function. So this system failure time, it means the largest order statistic, which will last longer, that should be the system failure time. So that's what it means by order statistic. Which I don't want to do that, but that's the whole concept. Any questions so far? So that's how far I want to go on the exam, nothing more than that. So at least I want you to know the right concept of order statistic and some concept of sum of the two random variables, discrete and continuous. I wish I would to let you go, but I can't afford it. I have lots of topics to cover, so let me just go ahead and start a little bit of chapter 4. A little bit of this, and I should be done with it.
Quick question.
Yeah.
So, are you gonna release like a narrowed down list of questions that we should focus on for the exam, like last time?
Not really this time, because last time, so personally, I don't think probability is that important for this content. So this is way more important, and I didn't want you to study something that's not that necessary. But this topics, I cannot do it. because everything you have to know. So as far as I can see, the questions on your homework list will be enough, but I don't think I can narrow it down to anything else. So in my Canvas, I've given you a list of topics, everything you have to know. So I'm not able to actually make a shorter list, unfortunately.
Oh, okay. Thank you. I was just wondering.
Mm-hmm. I wish I could, but I just cannot do. There's so many things you just kind of have to know. But once you know, you know it. It's a matter of just doing some calculation and some calculus. All right, so I want to go start a little bit of chapter 4, then stop there. So chapter 4 is about expectation. All right, so chapter 4, so it's about the expectation. So let's start with the definition first, and then we go from there. So let's go 4.1.1. So it's expectation of a discrete distribution. So let's go from there. So let's get the expectation, the definition. So let's go the definition. What does it mean by expectation? 4.1.1 and 4.1.2. So starting with the discrete case, so x is a discrete random variable with the mass function f of x. The expectation of x, so we denoted by e of x. It's a number. That's defined as the following. So e of x equals sum of all these values, x times f of x, for all the x values. So this e of x expectation is also called the mean of x. So some of you may have, in your stats class, you have seen this mean of x as mu for mean of x. So this is it. And also the expected value of x. I'm more used to calling expected value. All right, that was that. So let me get the note. If is e expected value or expectation of absolute value of x, it's infinity, then we say that expectation does not exist. So you may have a value or you may not have a value. So I want to get one quick calculation for this PMF case. So PMF of x. So x is going from 1 to 3. And the probabilities are 1/4, 1/4, and 2/4. So E of x expectation is sum of x times its probability. So 1 times 1/4, 2 times 1/4, and 3 times 2/4, which is 9/4. So that's a general form. So I'd like to get the Bernoulli random variable. So for the graduate students, you will actually have to remember the facts about some distribution. This is one of it. So x is a Bernoulli random variable. With parameter p. So we have x values are either 0 or 1, and the probabilities are 1 minus p for 0 and p for 1. So expectation for Bernoulli case is 0 times the probability plus 1 times the probability. So the probability of success is the expectation of this. So that was that. Then let's go continuous case. So that's 4.1.2. So we will replace all this summation with integration. So the definition, 413. So if x is a continuous random variable with PDF f of x.
I'm sorry, can you spell just a little bit?
Spelling or let's say continuous.
Okay, I'm good, thank you.
It's a continuous random variable with PDF of f of x. Then expectation of x equals, again, what do? We replace summation with integration. So that becomes, we're integrating from negative infinity to positive infinity, x times f of x with respect to x. All right, so that's expectation. So I want to go get one as an example. So here goes my PDF of x, which is f of x equals to x squared. I don't think this is the right PDF. I should go to x squared. No, 2x. Let's get 2x. That should do. So let's get 2x for x going from 0 to 1. So I want my e of x, which equals to, you're integrating, by definition, x times f of x. My support is going only from 0 to 1, so I go from 0 to 1, x times f of x, 2x, dx. So that must be from 0 to 1, 2x squared dx. So 2/3. So that's expectation. All right, let's get one more thing that I should be kind of done and for you to do the rest of it. So let's go 4.1.2, which is the expectation of the function. So let's get the theorem right away. 411 is saying if x is a random variable with either PMF or PDF, depending on the discrete or continuous f of x, then let y be some function of x, then e of y, which is e of g of x, is equal to, if it's discrete, you get sum of all g of x times f of x. For all the x's, if x is discrete. If it's continuous, then you do integrate from negative to positive infinity g of x, f of x, dx. So that's the theorem. So I want to get you an example, and I should be done for the day-to-day. So let's get the uniform case. So let's get the uniforms. X is uniform from 0 to 2. I want to find e of x and e of x squared. So first of all, I need to know my PDF of x, which is going from 0 to 2. It has to be constant. Then I have to get the height of the function. So my f of x must be 1/2 for x from 0 to 2. So your e of x, which is kind of saying what is the center of this distribution. So we're looking at the center as a mean as expected value. So anyway, you do integrate, by definition, x times f of x dx. In this case, you have to go from 0 to 2. Your x times your PDF is 1/2. So 1/2 times x dx. So it goes, again, 1/4 x squared from 0 to 2, you'll get number 1. So for the uniform case, the expected value, expectation, the mean is right there in the center, half right between 0 to 2. It's a fact. So let's get the facts on the side. For x being uniform from A to B, then e of x must be right in between A and B, so A plus B over 2. The average of the two. So I want to get this e of x squared. So e of x squared, by definition, that x squared times PDF of x. So in this case, from 0 to 2, 1/2 times x squared dx. So that should be 4/3. Right, something that you have to be watched out for. Let's get the general form. Let's get in general. Expectation of g of x is not the same as g of e of x. So what does that mean? The expected value of x squared is not the same as e of x quantity squared. They're not the same. So let's be clear. So I think this is how much I want to go. So let's not go too far. So it's about 8:08. So let me stop right here and I'll continue with the rest of it tomorrow. And I think we just have I think it's okay, it's doable. All right, so let me start. So